Hi, ladies and gentlemen. In the last classes, we have seen the events, joint events, then the probability, conditional probability, and the Bayes theorem, and we saw the different terms in them. Now, today we see another topic that is the theory of random variables. So let me start with that presentation. So the speech is organized into your learning outcomes, then the definition of a random variable, then a comparison between a random variables and probability. Then we will see how to quantify these random variables, or how to characterize these random variables with the help of probability distribution and density functions. Then we will see the properties of cumulative distribution function and probability density function, and then the summary of understanding. So in this video you will learn the definition of random variables, then you will learn the properties of cumulative distribution and density functions, then you will learn to draw the CDF and PDF of real events and some random electrical signals. So when you talk about random variables, if you look at the development of probability, that developed through games of chance such as gambling. So mostly this development was done by the French nobility, who had a pre-revolution time, the pre-French Revolution time. The French nobility had a lot of time and money to spare, and the French mathematicians developed the theory of probability through such observations in such games. So in such gambling games, the outcomes are linked with the payoff, like you toss a die and some payoff is associated with that. Just like we take the lottery ticket. When you take this lottery ticket, that is your outcomes, like whether you win or fail, that is linked with some payoff. So that payoff is very important here. So it is very imperative to have rules connecting the outcomes with payoff. Now we have to connect the outcome of a trial with the payoffs. So random variables are used for this purpose. Random variables are actually some definite rules that link the outcomes with the payoffs. So a random variable is a function with a domain omega, that is the sample space, and codomain, the set of real numbers R, that satisfies the condition that probability that the random variable x equal to infinity equal to 0, that is the extreme cases, probability that x equal to infinity and probability that x equal to infinity and minus infinity, that is equal to 0. And again the second condition is the set x less than or equal to lambda is an event for every lambda. Okay. So these are the two conditions. A random variable is a function with a domain omega, that is a sample space, and codomain all real numbers, because the payoff is in rupee or dollar, so that is a real quantity. So your codomain is the set of all real numbers, and such a rule, it is a rule between the outcomes and payoffs in such a manner that the probability of x being infinity and minus infinity, that is equal to 0. And the set x less than or equal to alpha is an event for every possible real alpha. So let us consider a game in which a coin is tossed and the player gets 100 rupees if the head turns up, or he loses 100 rupees if a tail turns up. So that's a game in which the outcomes like head and tail, they are linked with the payoffs. This fixed assignment between the outcome and payoff, that's called a random variable. Once this should be declared before the game, and this random variable, this is a definite rule connecting the payoff and the outcome. So there is nothing random about a random variable, and there is no way, it's not a variable also, it's a fixed rule connecting the outcome with the payoff. This name random variable is actually a misnomer. People used to call it a random variable and the name continued, and it is neither random nor a variable. Now, it will be very intuitive to consider random variables with a probability because, as I said earlier, probability is a function, random variable is also a function. Now, let us see the comparison. Both are functions, but the domain of probability is the event, that is, the subsets of the sample space. That is, you can assign probability to a head, a head or a tail, or the null event. You can assign probability to those four things when a coin is tossed. That is, all proper subsets of the sample space you can assign probability. But when it comes to a random variable, the domain is not the subsets of the sample space, but the sample space. Like I can have a random variable or a rule for, say, the event head or the event tail, not for head or tail or nothing. Okay. So you assign probability to the subsets of the sample space, and you have random variable. You connect that rule for the sample space. The domain is the sample space. And another point is the range of random variable is a set of all real numbers. But for probability, the range is the real numbers from 0 to 1. So range of random variable, it is actually the pay of some amount in rupees or dollar. It can be any real number. But for probability, that range is from 0 to 1, or real numbers from 0 to 1. And the third thing is it's a cardinal point. Probability is defined a priori. Like even performing the trial, you can assign probability to that. I can assign probability to a particular horse winning in a horse race, even before the horse race. It doesn't matter whether the horse race is conducted at all. But you cannot have a random variable that way, because random variable requires a trial. Only if the horse race is conducted, then I can bet on a particular horse and get the money, or lose the money, whatever. Okay, so probability is defined a priori, but RV requires a trial. It is something post priori. It is post priori. RV requires a trial. Now, we are always interested in knowing whether a particular random variable is below a certain threshold alpha. So, we have to quantify this thing. Say, for example, in a production industry, people may be interested in knowing whether the number of defective parts is below a certain threshold. Or in wireless communication, that is, if you move from one base station to the other, your signal drops. Okay, the signal gets faded, and you may at some point it will start crossing it will go below some threshold. So how many times it crosses threshold, I am interested to know whether the random signal, whether my wireless signal, which is a random signal, whether that has crossed a certain threshold. So if it crosses many times, then the fidelity of the signal is very poor, and I may lose the conversation. So I should make sure that the signal strength is good enough so that the conversation is uninterrupted. So likewise, for a civil engineer, he may be interested in knowing whether a strain in a particular area or a particular column is above a particular threshold or below that. So this probability that x less than or equal to some threshold alpha is a very important quantity in many engineering fields. So that probability that x less than or equal to alpha, that is called the cumulative distribution function of the random variable x. So that is usually denoted by capital F, and throughout this course we will follow this notation. Capital F with suffix capital X, meaning that this is CDF is associated with the random variable x, and the variable inside is alpha. So fx alpha, that is equal to probability that x less than or equal to alpha. That quantity, that's a probability value, that is called the cumulative distribution function. So I have another function, that is the derivative of the CDF, that is called the probability density function, that shows the density of the probability. So PDF or probability density function or PDF of a random variable x, that is a derivative of the CDF. Usually I denote with a small f. Here also I follow the same convention. Small f meaning that it's a PDF and not a CDF. X means it is linked with the random variable x, and alpha is the parameter inside that. So fx alpha, that is equal to d by d alpha fx, capital Fx alpha. So PDF is the derivative of the CDF. So fx alpha or CDF, that is the integral of the PDF. Okay, fx alpha is minus infinity to alpha, all possibilities of x with fx small x dx. That small x is a dummy variable. Once that integration is performed, it will end up as a function in alpha. So let us consider our earlier game in which a player tosses a coin, and if he gets 100 rupees for a head and he loses 100 rupees for a tail. So if I consider the CDF of such a random variable, so this is a game in which I assign this random variable this way. If head comes, the player gets 100 rupees, and if tail comes, he loses 100 rupees. So this is a cumulative distribution function of such a random variable. So it's very easy to draw that. This is alpha from minus infinity to 0, and this is from alpha from 0 to infinity. So if you look here, you can see that your loss is 100 or a minus 100, and your gain is 100. There is no loss below a minus 100. So what happens is you never have an outcome like this. From minus infinity to minus 100, there is no such outcome. Because I don't have any, I will not lose 200 rupees by playing this game. I lose, the maximum I lose will be 100 rupees. So below that, it is an impossible case. So the probability, because fx alpha is a probability. So here, for x less than or equal to alpha, if I consider my variable here, this alpha here, if x less than or equal to alpha, from minus infinity, we said that fx capital or fx minus infinity is a 0. So it starts with a 0 and it stays here up to this point. When it crosses this minus 100, say for example, if I look from here to the left, if I look here to left, if I say probability that x less than or equal to alpha, if I say, you can see that there is an event here, a loss of 100 rupees. When does that happen? When I get a tail. And what is the probability of getting a tail? Because it is half. So here at minus 100, this rises to 0.5 and stays that way. Now it stays here because for all these values, for x less than or equal to alpha, there is an event called the loss of 100 rupees, which is equivalent to my probability of getting a tail. Now, when it comes here, when it crosses this point, if I cross this point, say 100, if I look from here, say from this point to the left, that probability that x, if alpha is here, probability that x less than or equal to alpha, how many x are there? I have two possibilities. One is a loss of 100 rupees and the gain of 100 rupees. It is a probability of loss of 100 rupees is due to a tail, and the gain of 100 rupees that is due to a head. So it is either a probability of getting a head or a tail, which is nothing but it is a probability is a 1. So from here to here, because all things are considered in that, it's a probability of the whole sample space, only head and tail are there. It is the probability of getting a head or a tail. So from here it rises from 0.5 to 1, and it stays here up to infinity because it cannot exceed 1. There are only two events, and the maximum probability that can happen is 1. So it stays here from this point to infinity. It stays here from this point to infinity at 1. And if I take the derivative of this cumulative distribution function, then I get the probability density function. From minus infinity to minus 100, it is a 0, so the derivative is a 0. And at minus 100, you can see that there is a vertical edge going from 0 to 0.5. Derivative of that vertical edge is 0.5 minus 0, which is an impulse of height 0.5. Now I am talking about the probability density function, which is the derivative of my CDF. So at minus 100, this shoots up to 0.5. I get an impulse of height 0.5. And from here to this point, it's a flat function of value 0.5, the derivative of which is a 0. So from here to here, it is a 0. And here you can see that another vertical edge that is going from 0.5 to 1. there's a vertical edge going from 0.5 to 1. So the derivative of that is 1 minus 0.5. That is the increment is 1 minus 0.5, so it is a 0.5. So I see another impulse here of height 0.5 at 100. Then again it stays at 1, so the derivative of it is 0. So this is the shape of the probability density function. Here you can see that this discrete probability density function. You have two impulses happening at minus 100 and 100. Sometimes you call it the probability mass function instead of the probability density function. For discrete things, discrete PDFs, you call as a probability mass function, just another name. Now let us consider another game in which the random variable relates the outcome of a single throw of a die, a six-faced die. Say this actual payoff, this random variable is shown in this table. Here I have a toss of a die. If 1 comes, the player gets 10 rupees. If 2 comes, player gets 5 rupees. This plus sign indicates a gain and minus sign indicates a loss. And 3 means it is neutral. He doesn't lose or gain anything. He gets 0. And if it gets 4, he loses 5 rupees. If it is 5, he loses minus 10 rupees. If it is 6, it is jackpot. He gets 100 rupees. So if you look here, you can see that the lowest value is minus 10. So below minus 10, there is no loss. So from minus infinity to minus 10, this CDF stays at 0. Okay. And between minus 10 and minus 5, you can see that there is one event, that is a loss of a 10 rupees. Okay, loss of a 10 rupees. What is the probability of that? That is 1 by 6, so it comes this way like a step. And from between minus 5 and 0, if you see, I have two events. One is this getting a 4 and getting a 3. So I have this probability 3 by 6. Okay, this is 2 by 6 from here, because I have between minus 5 from minus 5 to 0, the value is a 2 by 6, not 3 by 6, I am sorry, it is 2 by 6, it stays here. And from between 0 and 5, the lambda value between 0 and 5, here instead of alpha I have written lambda. Another variable, it's just the name of the variable. From 0 to 5, if you say there are 3 cases, that is getting a 3, getting a 4, or getting a 5. So I have 3 cases, so the probability is 3 by 6. Then here it is 4 by 6, this way. At 10 it is 5 by 6, between 10 and 100 it is 5 by 6. And then when it reaches 100, when it crosses 100, you can see that all events are, all of the sample space is covered. So the probability goes to 1, 6 by 6, and stays that way up to infinity. So this is how the cumulative distribution function looks like. Now for the, if you look at the PDF, it will be the derivative of this. You can see impulses of height 1 by 6 at all these points, minus 10, minus 5, 0, 5, 10 and 100. You can see that these impulses are of height 1 by 6, just like in the previous case. At minus 10, minus 5, 0, 5, 10 and 100. I have 6 impulses of height 1 by 6. So this is how the probability density function or probability mass function in the case look like. Now let us consider the properties of the cumulative distribution function. Cumulative distribution function is a probability value, so it is always between 0 and 1. Fx value is between 0 and 1. Now it is always an increasing function. If you look back here, you can see that at my fx equal to this at infinity, this 0, and here it is a 1. So what happens is it is always an increasing function. It's always an increasing function. It is never a decreasing function. So fx value for minus 10 is less than that of minus 5. So it's always an increasing function. So what I can say is fx lambda 1 is less than or equal to fx lambda 2. I'm sorry, this is lambda 2. Fx lambda 1 is less than or equal to fx lambda 2. This is lambda 2 for lambda 1 less than lambda 2. And fx minus infinity equal to 0, that is a negative end, and fx infinity is a 1. Fx infinity is a 1. Okay. And if you look at the PDF, that is, the cumulative distribution function is the integral of the probability density function fx lambda over probability that x less than or equal to alpha over lambda, that is equal to minus infinity to lambda fx x dx, where small x is a dummy variable, and integral of the PDF function over all possibilities, that is a 1, because what is PDF? That is a probability density function. If you integrate the probability density function, what you get is you get the total probability, which is a 1. And small fx function is always a positive function, meaning that it's always greater than 0, because that function is non-negative. Fx lambda, small fx lambda is always greater than 0 for all lambda. So these are the properties of the probability density function. Now let us consider an electrical signal. Let us consider a triangular signal, a random electrical signal. Let us try to compute the cumulative distribution function and the density function for such a case. Now you can see that this is a periodic signal that is always positive. It's a triangular one with slope a by t, capital A by t, as periodic in t. Now let us consider some arbitrary alpha here. This is my alpha threshold. So let us consider this alpha varying from 0 to say infinity, because this function is always positive, so I don't have to consider a negative value. So from minus infinity to 0, this capital Fx value should be 0, because this is nowhere negative. So minus infinity to 0, the cumulative distribution function is a 0. And let us consider that this alpha is 0. Say this is coinciding with this dotted line is coinciding with my x-axis. Let us consider. So what is the probability that x less than or equal to alpha? Because it is very small. It is 0. Now let us move this up. Okay. Let us move this up. What is the probability that this Vt, this random variable Vt, is below this lambda? What is the probability that this x or this random variable, what is that, v, I should put x, it's actually v, this signal is below this lambda. So what is the probability of this signal being below lambda? That must be the area under this curve from here to this point, okay, that is this area divided by the total area of the signal, okay. This is the total area of the signal, okay, that is the total possibility. So this area divided by this area will be the thing. As I move this alpha from this point to say to this height, say if I move from 0 to say infinity, that is y equal to 0 to y equal to infinity. So what happens is the probability value will be rising from this point to say 1. What is this 1? Because when this alpha touches this amplitude A, the probability becomes a 1, because then the probability will be this area divided by the area. The areas are equal. Otherwise, it will be the area below this line alpha divided by the total area. When this alpha line touches A, it is 1. The probability becomes a 1. So from here to here, it rises linearly with slope 1 by A. And here at this point, when alpha becomes A, when it moves and when it touches here, the probability becomes a 1. Then if you move up, you can see that if it crosses A, then always this Vt is below this alpha. So the probability is 1. So it stays this way. Now, what is the probability density function for this? That will be the derivative of this cumulative distribution function. From minus infinity to 0, it's a 0. I don't have to think about that. Now, here you can see that's a straight line with slope 1 by a. So, it will be a flat thing with a height 1 by a. From 0 to a, this will have a this will be a flat pulse of height 1 by a, and from a to infinity you can see that this is a flat line, so that its derivative is 0. So from a to infinity it will be 0. You can see that the width of this pulse is a and the height is 1 by a, so that area under that curve is 1. So that makes it a probability density function. Area under that curve is 1. So such a density function is called a uniform type distribution. Okay, this is a uniform distribution because each event in this has equal probability. You can see from 0 to a, all events have equal probability of occurrence. So this is a uniform distribution. Now let us come to the end of this topic. So the summary of understanding. So in this video you learned the definition of a random variable and you compared it with a probability function. Then you learned the properties of cumulative distribution function and density functions. Then you learned to construct the CDF and PDF of real events and random electrical signals. And that is the end of this session. I thank you all.